Welcome back to Math with Business Applications. I am your instructor, Amy Fuchsteiner. This is the last presentation for Chapter 12. Chapter 12 is Unit 8, and we're dealing with annuities, sinking funds, and amortizations. Today, we are doing Section 3 from Chapter 12. We are going to look at sinking funds and amortizations. Basically, what payments do I need to either pay off an existing debt or drain an account or save for something? All right, our goals for this particular section are as follows. We need to define what sinking funds and amortizations are. We're going to talk for a minute about who uses them and when, and how they're different from the annuities that we've been looking at. We want to be able to calculate the amount of a sinking fund payment using a table. That means you have to find the interest rate per period, the compounding periods, and you need to identify the goal amount. We're also going to calculate the amount of an amortized payment using a table. That means, again, interest rate per period, compounding periods, and the debt that is being rectified or the account that's being drained. We also want you to be able to calculate the sinking fund payment using the formula and the amortization payments using the formula. As we have with the last two sections, we want you to be able to separate the amount that was actually invested and the interest earned to the total amount that is paid in or withdrawn. All right? So, sinking fund and amortizations. A sinking fund itself is the future value of a goal amount. So, a sinking fund is very much like a savings account. In this case, however, it's different from an annuity because you know the future value. You know how much you want to have saved. What you don't know is how much you have to put away each week. So these are known monetary lump sums that you're saving for, and you're attempting to determine the payment amount for college, for vacation, for retirement. So how much do I need to put away each month if I want to be saving for a college fund of $30,000? How much do I need to be putting away each month if I want to save for a $4,000 vacation? Or if I want $500,000 for retirement, how much do I need to be putting away in regular payments, right? That's a sinking fund. It's like a savings account. It uses the future value, right? The other one is an amortization. Now, an amortization is a lump sum that's incurred or deposited in the present that gets paid off or paid out over time. Equal payments are made at the end of each period, because all of this is ordinary, until the debt is gone or the account is empty. Most of us know amortization in terms of debt. You amortize your car loan or your home loan. A line of credit would be amortized. However, those are not the only things that can be amortized. If you've ever received a lottery win or an insurance payout or perhaps a scholarship, all of these things can also be amortized. Your retirement account will be amortized when you get to that point. So you'll save up for years while you're working, and then when you're not working, you'll amortize that retirement account, all right? We're going to start with 12.7, which is the sinking fund and using the tables to do it. So calculating the payment of a sinking fund using the table. Again, we're going to find the I, we're going to find the N, same as before. We're going to reach across the future value, because remember, the sinking fund is a savings goal. It deals with a future value. So we need table 12.1. Again, that's 372, 373, table 12.1, the future value for a sinking fund. Now, we're not going to multiply. Remember, we're trying to find the payment. Since we're trying to find the payment, we're going to take the goal amount and divide it by that future value table factor. Here's how it works. Molly wants to have $8,000 in 5 years. Her bank is currently paying 12% interest compounded quarterly. How much does she have to deposit each quarter to reach her desired goal? So keep in mind, these are ordinary and they're simple, which means whatever your compounded interest is, that's how often you're making payments. All right, those two are in sync. They are synced up. So our interest rate is 12%. I'm going to divide that by 4 to get 3% per period. Total number of periods would be 4 times a year for 5 years, or 20. So using the future value annuity table, 12-1, 372, 373. I'm going to go down the 3% column and find 20 periods. That table factor is going to be used to divide the goal amount. So the sinking fund payment, the amount that Molly will need to squirrel away every 3 months, will take her savings goal of $8,000 and divide it by the future value table factor of 26.87037. This means she will have to put away $297.73 4 times a year, every 3 months. And if she can do that consistently for 5 years, she will have $8,000 in that account. So if she does that, how much will Molly actually have contributed? Remember, it's a savings account. So every time she puts money into that account, she's earning a little bit of interest on it. She's going to put $297 away 4 times a year for the next 5 years. Sorry, I thought it was 3 years. For the next 5 years. This gives her a total amount of $5,954.6, which means Molly has contributed $5,954.60. She's going to have $8,000 in that account, but she will only have contributed the $5,954.60. The difference is your interest. The interest is the future value of that account minus how much she's invested, or minus her total payments. So we're going to take $8,000 and subtract the $5,954.60 to get $2,045.40. This will be the interest earned on that account. I have a practice table here available for you. I will go through the first problem, maybe the second one, but then we'll just leave it for you to go. So in this particular example, the future value of the account is to be $250,000. We know the goal amount. The interest rate is 8% compounded annually for 14 years. So 14 times we'll be able to make a payment. So our I value is going to be 8% divided by 1, or 8%. Total number of compounds will be 14 times, or once a year for 14 years, 14. So the table factor that we're looking up is 8% for 14 periods. Oh, hello. That didn't show up. Or 24.21492. I think I got a wrong order there in my animation. So we're going to take that $250,000 and divide it by that table factor of 24.21492 to get $10,324.21. The second row gives us a future value of just $1,500. We're going to compound quarterly at 12% for 5 years. So we've got 5 years to save up $1,500. The payments are only going to be every 3 months. So our interest rate will be the 12% divided by 4, because it's quarterly. So our I will be 3%. N will be 4 times a year for 5 years, or 20. So if we look that up, 3% for 20 periods, you should get a table factor of 26.87037. Remember, this is future value, so our table factor should be more than the number of compounds. When it's the future, our table factor should be more than the number of compounds, 20. When it's present, it would be less. But this is future. All right, so 26.87013. So I'm going to take that $1,500 and I'm going to split it into 26.870037 or $55.82. So that means that every 3 months for the next 5 years, she's got to find a way, or this person needs to find a way to squirrel away $55.82. And if they do that, then in 5 years, they should have $1,500. That works out well. But I will tell you, nobody gets 12% interest. 12% interest is just not really possible. All right. I'm just going to click through the next two here. And I think there it is. I knew that chart was going to come in. So I'm hoping you took that opportunity to try a couple of problems and make sure that you were able to do them yourself using the present value table, either 12.1 from your text or the printout that is included in the module for this particular unit. All right. Amortization tables, same idea, but they use the present value, right? Because in the amortization tables, you've incurred a present value or a present loan or a present winning that has incurred today, and the payments are going out into the future. So for an amortization table, you need the present value table. This is 12-2. Or if you're using a physical copy of the book, page 382, 383. The steps are the same as before. We're going to find the interest rate per period using the annual interest rate and dividing it by the number of compounds per year. We're going to find the total number of compounds. This is your N. We're going to then use the table factor from the present value table. Again, page 382, 383, table 12-2. Or the printable table from your assignment module. Once you know that, our amortized payment is again the debt amount or the payout divided by that table factor. So we're going to find the payment by taking the debt or the payout and dividing it by the table factor. An example here. Here we have a fisherman that's going to purchase a new fishing boat for $13,000. He makes a $2,000 down payment and finances the balance at his bank for the next 3 years. What amortized payments are required every 3 months at 16% interest to pay off this boat loan? So he's got 16% interest, and it's every 3 months, so that's quarterly. Our interest rate per period would be the 16% divided by 4, or 4%. Total number of compounds would be 4 times a year for the next 3 years. That's 12. The table factor that we're looking up is 4% for 12 compound periods. So using the present value table, I'm going to look down 4%. I'm going to go across for 12 periods, and at their intersection, we have 9.38507. This is our table factor. 9.38507. In order to determine his payment, I need to take his loan and divide it by the table factor. Well, there's a little bit of a trick to this one. His loan amount was not $13,000. He actually put down a down payment of $2,000, which means he only had to finance $11,000. His debt would be $11,000. And we're going to divide that by the table factor of 9.38507. This gets us $1,172.07. So every 3 months, he will need to make a payment of $1,172.07. That's every 3 months for the next 3 years. So how much is he actually paying back on this loan? So from his debt, how much is he actually paying back? How much of that would be interest? Well, he's paying $1,172.07 4 times a year for the next 3 years. So his debt is going to be $14,064.89. That's how much he's actually paying back. Now, he's got an extra $2,000 on top of that that he didn't finance, but we're not going to talk about that at the moment. The interest then that he's paying for the interest, remember, is the privilege of using somebody else's money. So, ooh, I don't like what that says. I need to switch that. We're in the middle of it, so I'm not switching it right now. I'm using this. I want green. Okay. So the interest would be his total payments. I need to switch that. Total payments. That's what you get for copying and pasting. Total payments minus the original debt. Okay. That's how we're going to find that. I will switch that in the original, but we need to make sure we got that clear. So what are his total payments? His total payments are $14,064.89, or $1172.07 times 4 times a year times 3 years. The original debt, I don't like what this, right? Because this was a debt, was $11,000. So we're going to subtract from that the $11,000. That gives us $3,064.89. So he's paying an extra because it was a debt and that's interest. So he's paid an extra $3,064.89 for the privilege of borrowing the money for this boat. Okay. I have available a practice table. This is an amortization payment practice table. So we're going to be doing the same things, finding the I and the N, and then the table factor. And in order to calculate the payment, we're going to divide the debt or payout amount by that table factor. So we have an 8% interest every 3 months. So that gives us an I value of 8 divided by 4, because every 3 months is quarterly, or 2%. Total number of compounds would be 20. So my table factor will be looking up 2% for 20 periods, and that's not on this particular chart, but that's going to be a 16.315143. So I'm going to take the present value amount, or $5,500, and divide it by 16.35143, giving him payments of $336.36. I am now going to go silent and let you do the rest. Hopefully you take this opportunity with a calculator and a paper and pencil and work a couple of these out. Make sure you know how to do them. Make sure you're using the table for present value, that is table 12.2, when you do the amortization ones. All right, let's take a look at the formulas. There are 2 formulas in this section, one for the sinking fund, which uses the future value formula, a slight inversion of that, and the other one for the amortization, which uses the present value formula, a slight inversion of that. So let's go. We've got the payment can be found by taking the future value times the net brick, again, I divided by, look at that denominator. Oh, that denominator is 1 plus I to the nth power minus 1. You have to find that entire denominator first. So the future value is your goal amount. How much are you saving for? How much do you want to have in the future? The payment is the regular payments that you need to make now in order to have that amount. Your I is the interest per period, same as it has been, and your N is the total number of periods. Okay? So using your calculator, please keep in mind that if you need help, you can contact myself, your embedded support personnel, or the Math Center. We will all help you with your calculator functions. Everybody has a different calculator, so it doesn't necessarily bode well for me to put something up here because you just use your phone anyway. If you're going to use your phone, remember to switch it. So you got it the long way, and you can find your power key. Okay. All right. As before, know your variables. You want to be able to identify your goal amount. How much are you saving for? What's the interest rate? How many compounding periods do you have? Can you calculate the I value and the N value? You need to be able to do all of those things. Make sure you're familiar enough with your calculator that you're using that you know where your answer key is, that's your last calculation. Second equals will bring up your last calculation. That you can use your power key, that's either the chevron or the y to the x. In some calculators, it's x to the y. And in some calculators, you just get a little box. Talk to somebody if you don't know how to use your calculator, all right? And then once you have that, you can also just use the order of operations. We're going to start with the innermost parentheses, doing I plus 1 or 1 plus I first, and then taking that answer to the nth power. Then we're going to subtract 1 from it. We're going to save that answer in our calculator, or we're going to write it down on our paper, but we need all of the decimal places. We're then going to take our interest per period and divide it by that long decimal. And that's going to give us the number in the brick. Once we have that number, we're going to multiply it by the future value goal. Okay? Here's a sample. Ski Swap will need $25,000 in 12 years in order to replace their heating unit. What payment every 3 months is needed if they get 2.8% interest compounded quarterly in order to amount to that $25,000 in 12 years? So we've got an interest rate. We know it's compounded quarterly. We know their payments are going to be every 3 months. That's also quarterly. We know they have a goal amount of $25,000. So we're going to find our I. That's the 0.028 divided by 4, or 0.007. Keeping in mind to convert your decimal or your percent to a decimal, right? Then what we have here is 12 years, 4 times a year. That's 48 total compounds. The goal amount is the $25,000. So into the formula, my payment would be that $25,000 times the brick, right? I just keep calling it the brick. I don't know what else to call it. So inside that brick, I'm going to have the 0.007 divided by that big honking denominator, 1 plus 0.007 to the 48th power minus 1. Substitutions are going to look like this. I'm going to start order of operations, and I'm going to do 1 plus 0.007, and I'm going to take that to the 48th power first. That's going to give me 25,000 times 0.007 divided by 1.397702 minus 1. So now I'm going to concentrate on that denominator because I can do the 1.397702 minus 1. And that's going to give me 2,500 times 0.007 divided by 0.397702. Now I'm going to do that division, 0.07 divided by 0.397702, to get 25,000, times 0.017601118. That's a long decimal. It ain't a happy one. Well, it's probably very happy, but it's not pleasant to look at. But I'm going to multiply that by the 25,000, to get $440.03, it looks like. So what does this mean? This means that every 3 months for the next 12 years, Ski Swap, whatever that is, needs to be able to put away $440.03. So if they do that, how much will Ski Swap be depositing in total? So they're going to do $440.03 4 times a year for the next 12 years. That's going to give them $21,121.44. They're going to need 25,000, and 25,000 is what's going to be there. The difference between the 21,121.44 and the 25 is their interest. The future value of this account is 25,000, and we're going to subtract out of that their total deposits of $21,121.44. That's going to give us $3,878.56. That is their interest, the difference between the future value and the total number of deposits. As with the last time I have practiced, we're going to use the same formula for the sinking fund payment. Our I value will be 9% divided by 12 for every month, or 0.09 divided by 12, or 0.0075. Total number of compounds will be every month for 14 years, or 168. The goal or future value is 55,000. So the formula will look like 55,000 times 0.0075 divided by 1 plus 0.0075 to the 168th power minus 1. If you're doing your order of operations, we're going to do 1 plus 0.0075. Enter. Raised to the 168th power. Enter. Minus 1. Enter. Now, you either need to store that number or you need to write it down on a sheet of paper. All of the digits. Don't skimp. Keep them all. 0.0075. Divide by that big long decimal. Enter. Now multiply by 55,000. You will need regular payments of $164.42. That is, in this case, $164.42 every month for the next 14 years. And if they do that, they will have $55,000 at the end of this particular problem. I'm now going to clip through the rest. Take out your pencil and paper, take out your calculator, clip it at 10 seconds, and go. All right, with the amortization formula, we get the return of the ugly negative n. All right, so much like your present value problems, we're looking at just sort of an inverse of the formula here. Our payment can be found. Remember, an amortization is a payment out into the future. You incur a lump sum debt or payout now that you take withdrawals from into the future, or you pay off with regular payments into the future. So the amortization formula uses the present value and multiplies it again by that brick. That brick this time is I divided by the entire denominator is 1 minus 1 plus I to the negative nth. So again, the PV stands for the present value. This is the debt incurred or the amount you have to take for the payout. The payment will be the regular payments made to pay down a debt, or in some cases to drain an account, a scholarship, a lottery winning, etc. I is the interest per period. N is the total number of periods. Again, be careful, it is a negative. That is a negative N, so watch out for that. Using your calculator, you want to be sure that you know your variables. That is, that you can identify, I'm going to need the debt or the payout, DEBT, or payout. Copy and paste has not done me good. That you can tell your interest rate, the number of compounding periods, and the time in years. You'll need this information to calculate your I value and your N value. Again, I cannot stress enough, know your calculator. You will need at least your answer symbol and your chevron or power key. It may be helpful to have your memory, to know how to use your memory function or the recall button on your calculator as well. We will be using the order of operations as I go through the examples of this. In the order of operations, you will start with the furthest in parentheses, the 1 plus I first. You will find that answer and raise it to the negative n power. You will need to find a way to record that number, either in your memory of your calculator or write down the digits. Don't skimp, write them all down. Then do 1 minus that long decimal. Again, don't skimp. And write that down. Now, you will need to take your I value and divide it by that last long decimal, the 1 minus 1 plus I to the negative n. That's, now, once you hit enter, what you've got is what's inside your brick, right? Now you need to take that and multiply it by the present value of the account. Again, if you need help, ask your instructor. That's me. I will happily do it. It just doesn't make sense to do it en masse because everybody's got a different calculator. So if you run into problems and you can't get help, feel free to reach out to myself. Tim will also help. And of course, the Math Center is always available. All right. Randy purchases a motorcycle for $8,500 with an amortized monthly payments over 5 years at 9.3% interest. We want to find the amount of his payments. His interest rate is 9.3%. I'm going to use the formula. So I'm going to do 0.093. And I'm going to divide that by 12. That's going to get me 0.00775. That's its interest rate per period. He's going to do 12 payments, or it's compounded monthly over the next 5 years. So that's 60 compounding periods. The debt that he has to pay down is $8,500. There's no talk in here of a down payment or front money. So I believe it's the full $8,500. We'll calculate Randy's payment using the amortization formula, present value times this brick of I divided by 1 minus the quantity 1 plus I to the negative n. And we're going to substitute our known values into this formula. So we'll have 8,500 times 0.0075 divided by that entire denominator of 1 minus parentheses 1 plus 0.00775, close parentheses, chevron key, negative 60th. Order of operations, I'm going to do this bit first. So that's going to get me 8,500 times 0.00775 over 1 minus 0.6292622262122. Now I'm going to take that denominator, I'm going to clarify that by doing 1 minus that decimal, or 8,500 times 0.00775. over 0.370737878. This will give me 8,500 times 0.020904257, or regular payments of $177.69 if I round to the nearest cent. So the question becomes, how much did Randy actually pay? Randy made payments of $177.69 12 times a year for the next 5 years. That tells me that Randy paid a total of $10,661.40 for this motorcycle. That is more than was advertised. That's why you sometimes hear people pay cash, right? Always pay cash, it saves you money. It's true. Randy had to amortize his payments and take it out over 5 years, and he's paying extra. How much extra is he paying? Well, we need to take his total repayment of $10,661.40 and subtract from that the debt of $8,500. This means that Randy has paid interest of $2,161.40. That's extra money. If he would have been able to pay cash, he would have paid just the $8,500. Why do people do this? To afford things they can't afford. I mean, or necessities, whichever. Practice table is available for this as well. Notice we've got a nominal rate of 10.6. We've got a present value of $22,500. So we've got a debt essentially of $22,500 that we want to pay out over 10 years at 10.6% interest rate. Right? One payment a year. So what's that? Hey, that's crazy. Oh, this is interesting. It's a table. I'll have to fix this. I don't know what happened here. And there we go. So we've got an interest rate per period of 0.106. Total time in years is 10, or once a year for 10 years. So my present value is 22,500. So when I put that in and substitute it into the formula, I get 22,500 times that brick of 0.106 divided by 1 minus 1 plus 0.106, the negative 10th. And we're going to do this part first on your calculator. So we're going to do 1 plus 0.106, hit enter, take that to the negative 10th power. So chevron negative 10, don't hit the minus, negative 10. And then I'm going to store or write down that entire number. Then we're going to do 1 minus, keeping all of those decimal places, type it in, or 1 minus recall. And then I'm going to store that number, that result. So I need to take now 0.106 divided by that stored or kept result to get what's in the brick. And then 22,500 times that number. And you should get $3,756.68. I have a sneaking suspicion that it didn't save changes I made, that's what happened. But we'll figure it out. I'll figure it out. I don't need to click through this one because essentially it's been done for me. All right. So here's a summary comparing the sinking fund to the amortizations. So the sinking fund is used for saving money. It's about the future monetary goal, and that's known. At the end of the time period, 3 years, 4 years, 5 years, your goal amount is reached, and you're trying to find the regular payments that will get you to that goal. Some common sinking funds are regular equipment replacement. If there's expansion or renovations, in a personal level, maybe it's a retirement account or a vacation home, who knows? You can use the future value table factor to find the sinking fund. The payment amount is found by taking the goal and dividing by that table factor. Or there is also a formula that is listed. It's future value times I divided by an entire denominator that is 1 plus I to the nth minus 1. Okay. The second option here is an amortization. An amortization happens when you have a debt in the present, or maybe a winning, some sort of an account that needs to be liquidized or carried out into the future. The present money is an obligation that hasn't occurred or a payout. At the end of your time period, 4 years, 10 years, 30 years, all of that debt or payout is gone and $0 remain in the account. What we're trying to find with an amortization is the payout that will make that happen. What is the debt repayment or the payout amount that will give you a zero balance at the end of those years? Some commonly amortized ideas: a mortgage, a loan. Those are all debt or obligations that get paid out. On the other side of that, it could be a payout for your insurance, a lottery winning. You could have a retirement account. You could have a scholarship that's paying you out over the next 2 years or 12 years or whatever. You can find the amortization payment by using the present value annuity table. If you take that obligation, debt amount, or payout and divide it by the table factor. Or you can use the formula where you use the present value, that is the current debt, obligation, or payout, multiplied by I divided by a denominator of 1 minus 1 plus I to the negative n. Whew, this is a good slide to write down or to keep an idea of, right? So is this last one. This last one is actually on the back. So if you print out the table 12.1 and 12.2, and then you look at the back of that, you actually see this decision square. So most often what happens with students is they can't determine what they're looking at. So here's what you do. What do you know? If you know the regular payments, so if you know how much the monthly payment or the quarterly payment is, and you need the value in the future, then you use the first square here. That's the future value annuity. If you know the lump sum and you're trying to find the payment amount, right? You know the lump sum, so you know how much you want to have in the future, and you're trying to determine what your payments need to be. That's a sinking fund. If you know the regular payments and you know how much money you have today, you know the regular payments, and you need to know how much you need to put away today in order to receive those payments into the future, then what you have is the present value. You're looking for the present value, right? If you know the lump sum, I know how much the debt is today. I know how much the winnings are today. I'm trying to determine the payment. Then you're looking at an amortization. Okay? So this is just a nice sort of little slide and or formula that helps you as you're looking over chapter 12 to determine which sort of formula you need of the 8 formulas that are in this section. So hopefully you find this helpful. It feels like the slide is a little messy to me. So again, I'm probably looking at something that didn't save. All right, so at the end of all of this, how do you feel? Confident? Do you know what sinking funds and amortizations are? Do you know who might use them and when? There we go. Can you determine how a sinking fund would be different from, say, a future value annuity? And how is an amortization different from a present value annuity? What's different about them? Do you feel like you could calculate the amount of a sinking fund payment from a table or an amortization? Do you feel like you could calculate an amortization from a table? How about the formulas for those guys? Could you do a sinking fund or an amortization from a formula? And do you feel fairly confident about being able to separate sort of these 3 ideas of what is the interest, what is the amount of the payments versus the amount that was actually invested? Do you feel like you could do those okay? All right. There is extra practice available in Chapter 12, Section 3. The entire review is what was covered in this presentation, so you would be all right with any of the exercises 1 through 25. If you have the physical copy of the book, I believe the pages are 391 to 394. You'll find the review there. There is a graded assignment in this section, as there is with all of the rest of the presentations. Again, oh so creatively labeled Chapter 12, Section 3. If you have any follow-up questions, if there is anything that you would like clarification on, please feel free to contact your instructor, your embedded math support personnel, or the Math Center. We all want to see you succeed, and we're glad you made it this far. This is the last presentation, and I hope you're able to get through all of this. All right? Thank you. Have a good night.